Hello and welcome to my presentation on the nested polytope problem is ER-complete. This is joint work with Michael Devons and Andreas Holmsen, and my name is Tilman Milzo, or just Tom. So let me define you what the nested polytope problem is. Here I give an example in dimension 2, and we've given an outer polytope here in red and an inner polytope here in blue, and a number here 5, and we want to know whether there exists a polytope. And 2-dimensional polytope is the same as a polygon with 5 vertices. And the green polygon is such a polygon with 5 vertices, which has 2 properties. First, it contains the blue one, and it is contained in the red one. So this is the nested polytope problem. Let's have a look at another example here. The outer polygon is a square, the inner polygon is a triangle, and the number is 3. Note that some of the vertices may agree of the inner and outer, and then a possible solution must also take those vertices. And then the third vertex could, for instance, be here at the bottom. That's the most right position, that's the most left position, but it could also be that the bottom vertex is in the interior of the outer polygon. Okay, let's look at an example of the nested polytope problem in 3 dimensions. Here the outer polytope is a cube. The inner polytope consists of 1, 2, 3, 4, 5, 6 points, and we've given them number 5, so we want to find the intermediate polytope with 5 vertices. So on the left plane, we must contain at least 2 vertices, actually at least 3 vertices, just to contain this blue triangle. And the same with the bottom plane. And in order to contain the blue point at the bottom here as well, what we have to do is we must contain also 2 points on the bottom plane. This is because we can't have a single vertex being at that blue point. You may wonder, okay, so I said the inner polytope here is given by these 6 points, so we take the convex hull of these points, and then we have given it. And the nested polytope problem can also be in higher dimensions, of course. So here I want to point out something interesting. So if you would given one of the vertices of the bottom plane, then the other would be determined, and there's a continuum of solutions for that instance of the nested polytope problem in 3 dimensions. Just to keep that in mind. Okay, so why would we want to study the nested polytope problem? There are 3 main reasons. The first one, it's a fundamental problem both in polytope theory and also in computation geometry. So it's a very easy to state problem that you can think of. If you would want to look for applications, you could think of, well, this has something to do with, I want to maybe simplify this outer and inner polytope. The intermediate polytope maybe is a simplification of both the outer and inner. So maybe if you were interested in applications, that would be an application. I think the most compelling reason to study the nested polytope problem is because of its very close relation to matrix factorization, and from there also to stochastic and to machine learning. So I want to explain here this relation to matrix factorization, and hope this is convincing to you. Okay, so in order to explain this close relation to matrix factorization, let me give a recap and cones. So this here is a cone, it goes here to infinity. If you have one vector in a cone, then also some scalars of it. If I have 2 vectors in the cone, also their sum must be in the cone. So this tells us if I have A and B as bounding vectors, then lambda times A is in a cone, lambda times B in the cone, and of course any of those sums, where lambda A and lambda B are scalars, positive, non-negative scalars. And the question is, can I get also every point in the cone like that? And the answer is yes. So let's see a way to see this. Let's draw these parallel lines. So we have this point, and I want to express this point in this way. And the way to do this, we draw these parallel lines, and then we see a simple way how we can express this point as a scalar of A and a scalar. Okay, so now that we have this recap, let's look now at non-negative matrix factorization. So I told you there's close relation to matrix factorization, and that now we want to understand. So let's look at what is matrix factorization. So we've given one matrix, and we want to write it as a product of two other matrices. And what we want is we want here the number of columns of this green matrix to be as few as possible. And then that is called the rank of the blue matrix. And if all the entries of the blue matrix are non-negative, then we could ask, what about the other entries? We want to have them also non-negative. And that is then in turn called non-negative matrix factorization. Okay, let's look at the geometry of that. So because we can only imagine things in 3 dimensions, I will just depict things in 3 dimensions. So the columns of the blue matrix, these are just vectors in some high dimensional space. Here, again, displayed in 3 dimensions. And then maybe I can find a plane that contains all of those blue vectors, right? Maybe they're all contained in this plane here. Then if I find 2 vectors which span that plane, then they can define me these 2 columns of the green matrix. So basically what matrix factorization is doing, it's trying to find a space in which all these blue columns live. This is what geometrically is going on. And then these here, they just tell me how I get from these 2 columns how they represent these people. So they're kind of redundant. Okay, so this is matrix factorization. So what is non-negative matrix factorization? First of all, note that all the vectors, they must be contained in the positive orthant. So that would be the condition, and then the solution, they should also be contained in the positive orthant. And because we have the third matrix also be non-negative, what we want that all the blue vectors are contained in the cone defined by the green matrix. So here I drew 3 vectors, although maybe we have them 2. Okay, so that would be the geometric meaning of non-negative matrix factorization. So how to go to the nested Polytope problem? Well, as we know, scaling all these vectors, it doesn't really matter, right? So we can just try to normalize everything. So we have here this plane which just says, well, the sum of all the coordinates should be 1. So that would be the normalization plane. And let's look at this normalization plane. So this red cone, the positive orthant is nothing else than a cone. It just becomes a triangle in 3 dimensions, or it would become a high dimensional simplex in high dimensions. And now if you intersect the blue vectors with our normalization plane, then this just becomes a polygon, or in high dimensions, a high dimensional polytope. And the green vectors, they really want to be, inside the red polytope, and they should contain the blue polytope. So really, if you look at non-negative matrix factorization restricted to the normalization plane, you end up with the nested Polytope problem. So the nested Polytope problem generalizes a non-negative matrix factorization. I hope that I could convince you of this by those nice looking pictures. Okay, and that's a close relation that I mentioned earlier. Okay, so let me go briefly through the related work that has been done so far on the nested Polytope problem. It was first mentioned already a long time ago, 1979, so that's before I was born, by Zilio. That's the oldest literature that I could find. Let's say, maybe first really interesting result is by Das and Joseph, who already showed in 1990 that the problem is NP-hard already for 3 dimensions, so you don't have to go up that many dimensions. This reduction that I showed you goes back to Cohen and Rothblum from 1993, that non-negative matrix factorization reduces to the nested Polytope problem. This is what I showed you just a moment ago, and which makes this nested Polytope problem really interesting. In 2009, this showed that the intermediate simplex problem is NP-hard. Here, the intermediate polytope must be a simplex instead of a nested Polytope problem, so that's a special case of the nested Polytope problem. Then there is, in 2016, it was first observed that irrational coordinates may play a role in an optimal solution. So there may be instances where the only way to place the intermediate polytope by using irrational coordinates, although the inner and the outer polytope are given by integers or rational coordinates. So this is by Dimitri and others, and somewhat in parallel, Shitov showed the same. It's not quite clear who was first. I think Shitov had an archive version, while they in parallel had the Eichelt and Soda version. So there was a little bit in parallel. But then Shitov, he showed that non-negative matrix factorization is complete for the existential theory of the reals. And together with the result from 1993, this implies that the nested Polytope problem is also ER-complete. So our result today is the nested Polytope problem is ER-complete. Let me point out that is not new, because it follows from the 2 papers I mentioned earlier, but we have found a simple geometric proof, which we hope is interesting by itself, and it's really a very different proof than the proofs that we saw from Shitov. In a way, it's simpler than the proof of Shitov, but I don't know. I guess it's a question of taste. Our proof is real geometric. Okay, so there are some other videos to show you more on ER-completeness, but let me just point out that there are various problems in computational geometry which are ER-complete, and this shows that under some mild assumptions, these problems are not contained in NP, so they're harder than NP-hard problems, and so either all of them are harder than NP, or all of them rely in NP. Okay, so but look at some other videos that I will post about ER-completeness. So how to show ETR membership? Well, the solution can be described by vectors, by real vectors, and then you have to encode that these vectors, the polytope described by these vertices, contain the inner polytope, and you should also describe how that each of those, you should describe that each green vector is contained in the outer polytope, and altogether they contain the inner polytope. So in this way you show ETR membership. So let me now give some sketch on how we show ETR hardness. So we show it in 2 steps. The first one, we reduce from the general ETR problem to ETR inf. This was already known, but we add a few twists to this, but mainly it was already known. And when we showed that this ETR inf problem reduces to the nested Polytope problem. So what is this ETR inf problem? ETR inf problem asked, we've given we ask whether there are real numbers which satisfy some set of constraints of the form x plus y equals z, or x times y equals 1. So that the ETR-inf problem and also ETR complete, so we can use it as our regression basis. So what I have to show you now for the geometric part, I have to show you how to encode a variable, how to encode this inversion constraint, how to encode this addition constraint, and then how to combine all of those things. Okay, so how to encode variables? Well, we saw already this example here, which I deliberately showed you in the beginning. So the red one is the outer, the blue one is the inner, and then what we would hope for is that the green one, it uses one of the vertices at this bottom segment here, and then we can say, well, if the bottom segment is here, we say that vertex is here, we say that corresponds to the value of half. If it is there, it corresponds to 2, and any value, any placement in between corresponds to a value between a half and 2. So this is what we want. Then it could encode variables. But it could, of course, be that there is one of the vertices at the top. But we saw in 3 dimensions, or that may not happen. Right? We found a way to force this guy actually on this segment. And that is how it looked like, right? So we remember what we saw earlier, really that vertex must lie on the segment because otherwise we can't see that thing. But also this, this instance that I showed you earlier, it is actually an inversion gadget, because if you look at the bottom plane, then if one of the vertices is fixed, the other is determined, and I claim that if this is x and this is y, they're the inverse of one another. So how to see this? Look at this triangle. So this length here is 1 and that length is 1. So you see here that 1 to x must be the same as y to 1. Well, this implies x times y. And thus, this is an inversion gadget. So now we have an inversion gadget. Great, it was pretty simple. So how to do addition? So here our segments somehow, they're horizontal, where we encode the variable, and we have somehow in the middle of our polytope, we have just one point which we want to contain, and then it turns out that these 3 variable vertices, they must add up. So we denote them by x, y, and z. They must add up to 5/2. So this is not exactly the addition gadget that we had before, but it's an addition gadget, and it will turn out to be sufficiently complex from an algebraic point of view. Okay, and so furthermore, note that here I've hidden on how to encode that x actually is on the segment. We kind of assume that this can be done. So now we need to combine many inversion gadgets and many addition gadgets. So let me show you how to combine different inversion gadgets. So let's assume we have lots of segments which contain a variable, and they're all in pretty high dimensions, and they're all orthogonal to one another. So this segment contains a point, and this segment contains a point, this segment contains a point. If we want to have an inversion constraint, we just put a blue point on the plane shared by those 2 segments. And if we want to have between those 2 inversion gadgets, we would add a point here at the correct location. But if we don't, we just don't add a point. So this is nice. So we can combine very nicely many inversion constraints. How to add addition constraint? So let's imagine we have here very high dimensional simplex, but I just imagined in 3 dimensions, and then in going one more dimension up. So here we imagine this being in 1 dimension higher. We do these segments which all contain a variable, and then if we want to have addition constraint between 3 of these variables, we just put a point at the corresponding on the corresponding face, just a little bit higher, And you can see that all of those, they don't interfere with one another. And this can be done if you have many enough dimensions. Okay, so now how to combine addition and inversion. And here really, it's a little bit magical. If you're comfortable with high dimensions, it's fine. If you're not comfortable with high dimensions, it's like, it's magic. So just accept that, you know, in high dimension things work nicely. So let me do this first in the very low dimensional case. So here we have an addition constraint, and we do orthogonally for this vertex we do an orthogonal variable, and for this vertex we do an orthogonal variable. So we could put another inversion constraint between those variable segments which share an endpoint, and to those which are parallel we could add another addition constraint if we wanted to do. This is kind of maybe doable here in 3 dimensions, but we just lift this and do this for arbitrary dimensions. So we have this simplex again, and at each one, you know, we can do this addition constraint, but at each vertex we do many variable segments which go into many dimensions, and to the corresponding dimensions you can add corresponding addition gadgets. So what we get is we get this matrix of variables. So at each vertex we have like a column of variables, and to each direction, for each these directions here, let's say the up direction, right, we get one variable, and this corresponds to a row. So if these variables are all in the same row, we can make some addition gadget to it without inflicting any conflicts with something else. And for each column, we can make arbitrary inversion gadgets as we like, without conflicting any conflicts, because all of this will be separate in separate dimensions. And now you see, we cannot make arbitrary addition constraints between arbitrary variables or between, but it's sufficient that we can make this with variables within one row and inversion constraints within variables within in one column. Okay, it's a little bit magic here because you have to be able to imagine things going in higher dimensions. But yes, in this video I hope to give you the gist of the construction. Okay, so before I finish this, let me give you some open questions. So can we analyze this problem in smooth analysis? Is there ETR hardness already in fixed dimension? Can we show ETR hardness for the intermediate simplex problem? And are there tight ETH lower bounds? Okay, if you manage to attack any of those problems or solve any of these problems, please let me know. Yeah, if I solve maybe I've solved already one of those problems, but have not put them up online yet. So maybe contact me before you work on them, or at least if you found a solution, it would be nice if you could contact me. Okay, thanks a lot, and thanks for your attention, and I hope you enjoyed this video.